Welcome students. So today we start our new chapter, that is coordination compounds. Now in the coordination compounds there are majorly two species. One is the corresponding metal ion and the other one is the corresponding ligand molecules. So this metal ion is generally behaved as a Lewis acid and this ligand is generally behaved as a Lewis base. And when the metal ion is combined with ligand in a fixed manner, then that particular compounds are known as coordination compounds. Fine. Now there is Werner's theory of coordination complexes. So what are the main postulates of Werner's theory? The first postulate is that metal ion has two valencies. Metal ion has two valencies. Second postulate is that first valency is the primary valency, which is ionizable and variable. Third point is that second valency is the secondary valency which is non-ionizable and non-variable. Means we simply say that the primary valency of metal ion undergoes somewhat change, but in the case of secondary valency it has fixed number, it does not undergo any change. And this secondary valency is also known as coordination number, which is fixed for each metal ion. For example, for the case of zinc, copper, this secondary valency is 4. For the case of iron, either it is ferrous or ferric, or cobalt, chromium, platinum, it is 6. For silver and gold, the secondary valency is 2. And for nickel, in some complexes this valency may be 2 or this valency may be 4. Fine. So there are general 3 points. It has 2 valencies. Primary valency is ionizable and variable. Secondary valency is non-ionizable and non-variable. Now if I represent one coordination complex compound, so this coordination complex compound is shown by a square bracket in which the corresponding metal ion is represented by the corresponding ligand molecules, and the value of x is secondary valency or coordination number. Fine. And if I represent another part in this complex, for example this is y and this is z, then y is simply the primary valency, or we simply say that it is representing the corresponding oxidation number of that particular metal ion. Fine. So this x value is always constant, or it is always fixed for the metal ion, but the z value is going to be changed. It is somewhat variable and ionizable. For example, if I take an example of this complex K4 Fe CN6, K4 Fe CN6. Now what is iron? Iron is central metal ion. Fine. What is Cn? Cn minus is the corresponding ligand molecules. What is potassium? Potassium is what? Counter ion. Fine. And this 6 number is the corresponding secondary valency, which is always fixed. It does not change somewhat. And in this complex ion, iron is present in +2 oxidation state. Now if I ionize this compound, then this whole part in a square bracket, or we simply say that this part, this square bracket part is known as coordination sphere. So when I ionize this complex compound, this coordination sphere part does not undergo any ionization, or I simply say that this secondary valency or coordination number is completely non-ionizable. This is the main point. Only the outermost part, in this case this Y part, or only in this case potassium ions undergo ionization. Fine. So when the complex is formed, it forms in this way: K positive plus Fe CN6. Now It contains plus 2 oxidation state. Fine. It contains minus 1 oxidation state. Plus 2 minus 6, how much charge? Minus 4 charge. So this minus 4 is balanced by 4 potassium ions. Because each negative ion is balanced by a positive ion, this means that the charge on positive and negative ions must be equal. So in this case, this is the complex ion, or this is the simple ion. Fine. If I take another case, for example, if I take this case, zinc, Ba2. Fine. Now in this case, cation is somewhat simple and anion is somewhat complex. Fine. But in this case, cation is complex and anion is simple, because on ionization it reduces the corresponding bromide ion, Br minus, and this is the corresponding complex cation. So it is complex ion, and this is simple ion. Fine. Now how many bromine are there? 2 bromines. So one bromine contains how much charge? Minus 1. So 2 bromine contains how many charge? Minus 2. So this minus 2 charge is balanced by the charge on this complex cation, which is plus 2. So in this way they undergo ionization. Now what we learn from this ionization is that only the outermost ion undergoes ionization, and the ions present in this complex does not undergo any ionization. This means that this ammonia is non-ionizable, this cyanide is non-ionizable, this iron is non-ionizable, this zinc is non-ionizable. Only bromide and potassium ions are ionizable because they are written outside the square bracket. This is the main concept. Now if I discuss some other part of coordination complexes. So if I describe these coordination complexes in the corresponding salts, salts means if I classify these complex ions in the corresponding salts. So first category of salts is simple salts. Second category of salts is somewhat complex salts. And third category of salts is double salts. So from lower standards, we heard some simple salts, for example, sodium nitrate, KCl, K2SO4, zinc oxide, MnO2. All these are simple salts. They contain simple ion, simple cation, simple anion. Simple anion may be normal ion, or simple ion may be oxo anion. Similarly, in the case of complex salts, either cation is simple and anion is simple and anion may be, or if I write in this way, cation may be simple. Simple means either it is one single ion, sodium, potassium, rubidium, any ion, iron, chromium, cobalt, in this way. So cation is somewhat simple and anion is complex. Anion is complex. Second example is what? Cation is complex. or anion is simple in this way. And third part is both the corresponding ions are in complex form. Complex, both cation as well as anion. Fine. K4FeCN6. K4FeCN6 means potassium is present in simple form and FeCN6 part is the corresponding complex anion. ZnNH34Br2. So ZnNH34 is the corresponding complex cation and the bromide ion is a simple ion. Similarly, if both are present in their complex forms, then it is complex cation and complex anion. We simply say like that. Now, what about double salts? So double salts are the mixture of one anion with two positive ions containing water of crystallization. Fine. So if I take the example of double salt, then best example is potash alum. What is the formula of potash alum? K2SO4 dot Al2SO4 whole thrice dot 24H2. So in this potash alum, sulfate ion is the common ion, that is one anion, and there are two different positive ions, one is potassium and one is aluminum. So this is an example of double salt. Similarly, if I take an example of carnallite, so carnallite is double salt of potassium and magnesium chlorides. This is carnallite. One is chloride ion and other two are positive ions. Fine. And what is the difference between the corresponding complex salt and double salt? In the complex salt, the corresponding elements which are written in the coordination sphere does not undergo any ionization. That part we discuss now. But in this case, in double salts, for example carnallite, when it undergoes ionization, then potassium ions are there, chloride ions are there, and magnesium ions are there. Means all are ionized. Fine. But when I take the example of this type of salt, this is complex salt. So in this case, which ion undergoes ionization? Sodium, cobalt or fluoride. So when ionization takes place, only those ions which are written outside the square bracket or outside this coordination sphere undergo ionization. The rest part is inside this coordination sphere. So only sodium ions undergo ionization and this square bracket part remains non-ionized. There is the main difference. But in double salt, all ions undergo ionization. Fine. Now if I discuss some part of ligands. What are ligands? Ligands are generally electron-rich species which donate their electron pairs to central metal ion and forms the corresponding dative bond or coordinate bond. Now, we simply say that ligands are electron donor species that donate an electron pair to central metal ion. Fine. Now there is also one term with respect to ligand, that is denticity. What is the meaning of denticity? Denticity is simply the number of electron pairs donated by the ligand molecules. For example, if ligand molecule donates one electron pair, then it is monodentate. 2 electron pairs bidentate, 3 tri, 4 tetra, 5 penta, 6 hexa, in this way. So we simply say that one part is monodentate, other part is bidentate, and after that we simply say that polydentate ligands, more than 2. So if only one electron pair is donated, then it is monodentate. If 2 electron pairs are donated, then bidentate. And obviously, if more than 2 electron pairs are donated, then it is polydentate. Fine. Now, if I classify monodentate ligands, now these monodentate ligands are classified into 3 types. One is anionic, second one is neutral, and third one is cationic ligands. Fine. In these molecules, only one atom is there which donates its corresponding electron pair to metal ion. So they are regarded as monodentate ligands. Now in anionic ligands, many examples are there. For example, O minus 2, O2 minus 2. Similarly, Cn minus, halide ions. O minus 2 is what? Oxide. It is peroxide, cyanide, halide, sulfide, hydroxide, fine. Similarly, if I write more examples, then N3 minus nitride, N3 minus in this way azide. Fine. Neutral ligands include neutral molecules, for example water, neutral, ammonia, neutral, pyridine, neutral ligand. And cationic ligands mainly include NO2 plus or NH2, NH3 plus. NO2 plus is what? Nitronium ion. And N2H4 is what? Hydrazine. But this is NH2 NH3 positive. NH2 NH2 is hydrazine, and this is NH2 NH3 positive. Therefore, it is known as hydrazinium ion. Fine. So all these molecules are those molecules which contain their one electron pair to donate. Therefore, they are known as monodentate ligands. Similarly, if I classify molecules to bidentate, so main examples of bidentate ligands are first example is EN. EN is known as ethylene diamine. What is the structure of ethylene diamine? This is C H2CH2 part, that is ethylene, and this is corresponding amine. These are the corresponding lone pairs which are donated by two nitrogen atoms. So it is bidentate. Second example is oxalate, the famous bidentate ligand. C2O4 -2, C double bond O minus and O minus. These two donate their electron pairs, so it is also an example of bidentate ligand. Similarly, glycinate ion. So glycinate ion is this type of ligand in which nitrogen and oxygen donate their electron pairs, and it is an example of unsymmetrical bidentate ligands. Unsymmetrical bidentate ligands. Now, this is an example of unsymmetrical bidentate ligand, and these two are examples of symmetrical bidentate ligands. Fine. Now there is also one famous ligand which is known as EDTA. What is the meaning of EDTA? EDTA simply means ethylene diamine. Ethylene diamine tetraacetate. Fine. So what is the structure of ethylene diamine tetraacetate and what is the density of this ligand? So up till now we discuss all these ligands. Now what is the structure of ethylene diamine tetraacetate? First you write ethylene diamine, this is CH2 but this is two amine groups. Now when I compare the structure with this structure, there are two hydrogen atoms which is attached to nitrogen. Now when these two hydrogen atoms are replaced by the corresponding acetate ions, when these hydrogen atoms are replaced by acetate ions, then the structure is formed in this way. CH2 C double bond O negative, in this way. What is the formula of acetic acid? CH3COH. So acetate ion is COH or COO minus. So acetate ion is COO minus. Similarly there also CH2 C double bond O negative. There also CH2 C double bond O negative. And there also CH2 C double bond O negative. Now when I see the structure of this ligand, we simply locate that which atom donated its lone pair. Now there are 6 atoms which donate its lone pair to the corresponding central metal ion, due to which this ligand is hexadentate ligand. Fine. And if I go to all these monodentate ligands, so in monodentate ligands we simply see that this oxygen atom donated its lone pair, oxygen atom donated its lone pair, carbon donated its lone pair, halogen donated its lone pair, sulfur, OH minus ion in this way. When I draw the structure of hydroxide ion, then this is oxygen, this is oxygen, this is hydrogen. And there is negative charge. So this electron pair is donated by oxygen, so it is also monodentate ligand. Hydrogen does not have any lone pair, so it cannot donate its lone pair. Water is there, 2 lone pairs are there. Ammonia contains 1 lone pair on nitrogen. Pyridine is this structure, C5H5N. This is pyridine. And in the case of carbon monoxide, one example is also carbon monoxide. So if I draw the structure of carbon monoxide, then it is C, and there carbon act as that particular atom which donates its electron pair. So CO is also one molecule in which the corresponding donating electron pair is carbon rather than oxygen. Fine. NO2 plus. So in the case of NO2 plus, if I draw the structure, nitrogen, oxygen, in this way, so it donated its lone pair. This is NO2 plus, and it is neutral oxygen and is somewhat negative part. And in the case of hydrazine, if I draw the structure, then it is in this way. NH2 NH2. Now what I have to do is that I just replace this lone pair and place one hydrogen there, by which it possesses positive charge. When it possesses positive charge, then only this one nitrogen atom is there which donates its lone pair. So only one atom is involved in donation of lone pair or donation of electron pair. Therefore it is also an example of monodentate ligand. Fine. Similarly, in all these ligands also, there are two atoms which donate their lone pairs, and in this ligand there are how many atoms? 6 atoms are there which donate its lone pair. Now there is one question that up till now we discussed that the corresponding metal ion has fixed valency known as secondary valency or coordination number. Now my question is that in the case of complex of chromium Cr H2O6 Cl3, this is one chromium complex Cr. Now if I replace this water molecules with, suppose, ethylene diamine Cl3 or Cr, EDTA, fine. Now EDTA contains how much charge? How many charge? -1 -1 -1 -1 means -4 charge, and chromium contains how much charge? +3 charge. So 3 minus 4 is -1 charge. So this -1 charge is balanced by placing one potassium. Now my question is that in all these complexes of chromium, what is the coordination number of chromium? This is my question. Now water is there. One water molecule donates its one lone pair. So 6 water molecules donate their 6 lone pairs. This means that 6 dative bonds are formed with this chromium atom. Therefore, in the first case, coordination number is 6. No doubt at all. Now, there are only 3 ethylene diamine ligands are attached with chromium. What is the meaning of that? This means that only 3 coordinate bonds are formed with chromium. This is correct or incorrect? Now we know that ethylene diamine is a monodentate or bidentate ligand. Ethylene diamine is the famous example of bidentate ligand in which a single molecule contains 2 donating atoms which donate their electron pairs. Now if a single molecule contains 2 atoms, this means that 3 molecule contains 6 atoms. Or if I attach the corresponding 3 molecules of bidentate ligand with chromium, then one molecule forms 2 dative bonds. This means that 3 molecule forms another, again, 6 dative bonds, or the coordination number in both the cases is 6. Similarly, in this case also, chromium is bonded with EDTA. Now this single molecule contains 6 donor sites. 6 donor sites, or we simply say that in this case also the coordination number of chromium is 6. Therefore, we simply say that the coordination number or the secondary valency of central metal ion is fixed. It cannot change. What the thing changes? The corresponding number of counter ion or the primary valency. Fine. So up till now we discussed the ligands part depending on their donation of electron pairs. Now there is also one concept. There is also one concept of ambidentate ligands. What is the meaning of ambidentate ligands? If there are two donor atoms in an ion, or if I say that in this species, then at one time only one atom donate its electron pair. Fine. Means what I want to say is that if there are two donor atoms in one species, then with central metal ion only one atom is involved in the formation of dative bond. For example, if I discuss the example of NO2 minus, now NO2 minus is written in this format. Either this molecule is the corresponding nitro, or either this molecule is in the form of nitrite. So when I write the corresponding name nitro, this means that nitrogen atom is involved in the formation of dative bond. When I write the name nitrite, then oxygen is involved. For example, if the structure is formed in this way, so in this way, when oxygen atom is donated its lone pair or electron pair, then this term is used because oxygen is involved in the formation of dative bond. But if nitrogen is involved in the formation of dative bond, then in that particular case we use the term nitro. So it is an example of ambidentate ligand. Simply, if I write in this way, Cn minus. Now Cn minus also contains this part. If carbon is involved, then it is cyanide. Fine. And if nitrogen is involved, then it is isocyanide. For example, C triple bond N. Now carbon donated its lone pair, so the name cyanide is used. If nitrogen donated its lone pair, then isocyanide is used. Simply, there is also one example of this part, SCN and NCS. If sulfur donated its lone pair, then the name is thiocyanate. Thio word is used for sulfur. And if nitrogen donated its lone pair, then it is thiocyanate. There is the main difference. Fine. So depending on that which atom donated its lone pair, these ligands are classified as ambidentate ligands. Monodentate ligands only contain one atom which donated its lone pair, but they contain two atoms, but at one time only one atom is involved in the formation of coordinate bond. The rest part of this chapter we discuss in the next class.